We've been introducing things into our language that are adding power to our language. We started with simple objects. We introduced the notion of doing conditionals on them. That gave us branching programs. We then introduced iteration. We then generalized that to functions, which let us do things like writing both iterative and recursive functions. And then we've introduced the first of our compound kinds of data structures, tuples and lists. We're now going to build on those ideas in two different directions. First, we're going to talk about how we can use functions themselves as objects. Sounds a little strange, but it's really valuable. And then we're going to introduce an even more powerful kind of data structure called a dictionary that's going to give us the same kinds of abilities as lists, but add other things in. So let's look at that. I want to start by going up a level and talking just for a second about functions. In programming languages, we refer to functions as first-class objects, something that's nice to aspire to. What does it mean? It means that it has a type. It also means that it can be used as elements of data structures like lists. And finally, it means that it can be used inside of an expression. It could be part of an assignment statement or as an argument to a function. And I say that because in some ways, functions can be used the same places we would use numbers, or we would use strings, or we would use lists. Numbers have a type. They can be elements of a data structure, and they can appear inside of expressions. Same thing with strings. It turns out functions can as well, and that leads to some really interesting kinds of behaviors that we might like to be able to use. And it's particularly useful when we want to use functions as arguments coupled together with doing things on lists. We often refer to this as higher order programming. We're using functions, for example, inside of lists to do things on lists. And let me show you an example of that. Here's a nice little function. It's called apply to each. You can see from the doc string, it assumes two things. It assumes that L is a list, and it assumes that F is a function. And it's going to mutate L by replacing each element with that function applied to that element. The loop is sort of what you'd expect. I'm nicely iterating down the length of the list. And I'm saying basically for each index that goes into the list, get out the element of the list, apply F to it, and then put that back in that spot inside of the list. So I'm literally applying that function to each element of the list. Remember, I'm also mutating the list as I do it. So let's look at a little example. Imagine I have a list, L, that's 1, -2, and 3.4. I have my little function apply to each. And I first say apply to each, apply that to the list L with the function abs, or absolute value. What it will do is walk down the list, applying abs to each element in turn, so that when I'm done with that, L now has the structure shown on the slide. They're all positive. I could do the same thing. Apply int to each of them. 1 and 2, of course, are already ints. 3.4 gets truncated to just being 3. If I've defined factorial, which we talked about in an earlier lecture, I could apply that to each element of the list and get 1, 2, 6. And if I applied Fibonacci, which I defined in an earlier lecture, to each element again, I would again mutate the list. All right, a little funky, but what am I doing here? I'm now able to think about doing something to each element of the list, just as an operation. Apply to each is literally saying, given a data structure, give me back a version of that data structure. In fact, it's pointing to the same thing, but give me back that data structure where I've done something to each element of the list, in this case, using a function. Handy tool to have. I could do it the other direction, which is I could apply a list of functions to a number. Again, I can loop over that list, and in this case, apply functions is assuming that L is a list of functions. And it loops over it. It says for each element of that list L, apply it, assuming it's a function, to the argument x, and print out the result. And so if I do that now with, again, abs, int, fact, and fib on 4, it prints out the absolute value of 4, the integer portion of 4, factorial of 4, and the Fibonacci of 4, treating the functions as if they were themselves first-class objects, and simply giving it a list of functions in this case, a perfectly reasonable thing to do. That idea I can generalize, and in fact Python provides a very nice generalization, something we call a higher order procedure. It's called map. And here's what map does. In its simplest form, it takes a function that has, in fact, expects only one argument. It takes a collection, in this case, a list of appropriate arguments, and it literally creates a list where it has applied that function to each element in turn. So it will return an iterable that we need to walk down. And in fact, I can do that. Having done that map, it gives me back a collection of them, and I could walk down them in turn, printing them out. And it'll print out, in fact, the values of all of those pieces. I want to say that again, because in the previous case, I was mutating a list. Here, map gives me back a structure that's going to act like a list, but it's something that I have to walk down, iterate over to get back out. That's okay. In this case, I did it. If I wanted to convert it into a list, I could walk down it, accumulating results into a list. So map's a really nice way of abstracting this idea of applying something to a collection. In fact, map has a more general form, which is I could give it a collection of functions that expect more than one argument, what we would call an n-ary function, because it expects n arguments. And if I give it, for example, 2 lists, I can map a function down those pairs of lists, and what it will do is take the first element of each list, apply that function to it, take the second element of each list, apply that function to it, and generate for us something that has the result of doing that processing. And in this case, it's giving me the minimum of the 2 lists in each place, as you can see here. There's the minimum, there's the minimum, there's the minimum. And it reduces for me something that has that particular structure. Map, a very nice generalization about thinking about using functions just as if they were objects that can be applied in appropriate places.